Alright, so today we're going to be talking about solving quadratics by graphing. So yesterday we learned about graphing quadratics in standard and vertex form, and now we're going to talk about finding their solutions using these methods. Our goal today will be to solve a quadratic by graphing. Now I do want to let you know that just like with linear systems, graphing is not the most accurate or straightforward way to find a solution to a quadratic. And a solution is also known as the zeros, the roots, the x-intercepts, same thing as with linear equations. It's not the most accurate, and it's not the fastest way to find solutions. So we're going to look at these options, and then we're going to learn, okay, well there's got to be a better way, and that's what we're going to talk about after this lesson into the next few lessons. So solutions to a quadratic come in three different forms. The first form is that you have no real solution, and this occurs when the quadratic will never cross the x-axis. Okay? And there's two ways that this can occur. Either your quadratic is a positive quadratic that starts above the x-axis, or it's a negative quadratic that starts and goes downward below the x-axis. So in both of those cases, neither quadratic will ever cross the x-axis, meaning it has no real solution. Now you'll specifically hear we say the word no real solution. That doesn't mean there isn't a type of solution. We call that an imaginary solution, which we'll talk about in future lessons. But just keep in mind that means we have no real solution. Now whenever we have one real solution, that means that the quadratic hits the x-axis only once. And whenever you have only one real solution, your one solution is also your what? Yeah, it's also my x-intercept, but it starts with a v. It's also my vertex. Yeah, so whenever you have one real solution, that means that your x-intercept is also your vertex. That's a common question I've seen asked on SAT prep, where they say, in what case of a quadratic is the vertex also your solution? Something like that along those lines, so keep that in mind. And then the most common one we usually talk about in most classes is the two real solutions, which is what you had seen in Algebra 1. Probably most likely you probably saw a few one real solutions as well. But two real solutions means we hit the x-axis twice. Now if you were to draw the axis of symmetry in here, you'll notice that the axis of symmetry is equidistant to the two x-intercepts. See what I'm saying? Alright. Alright, so for example 1, we're going to look at the number of solutions, and then we're going to identify the roots, also known as x-intercepts. So how many solutions do we have in example 1? Just one. And then what would be the coordinates of that solution? 3, 0. And roots also may be written in the form x equals 3. Now moving on to number 2. If you look really closely on this one, how many solutions are there? Good. And then what are the coordinates? Good. 2, 0 and 3, 0. And roots can also be written in the form x equals 2 and x equals 3. Alright, so moving on to the next page. Once again, you guys try these ones. We'll just quickly go through this. Two solutions for this one, and the roots are -6, 0 and -1, 0. Can also be written as x equals -6 and x equals -1. This one has no real solutions. So when you're talking about quadratics and we name the number of solutions, if there are no solutions, make sure you write no real solutions. Because technically speaking, there is a solution. It's just imaginary, which we'll talk about next lesson, or next few lessons. And there are no roots, no real roots. Okay. So for example 3 and example 4, our goal is going to be to graph both of these quadratics. And then to graph those, we're going to use the graph to help us identify the x-intercepts. So we're going to go through the same procedures we learned about yesterday. If you're in, what form is this quadratic in for example 3? It is in standard form, right? So with standard form, if we want to identify the vertex, we first have to find the axis of symmetry. So we have to find the axis of symmetry, which is x equals negative b over 2a, which means in this case it's going to be 1, because it becomes a positive, over 2 times 1/2. Well, 2 times 1/2 is 1, so we have 1 over 1, which is 1. So I know that the x-coordinate of my vertex is 1, which means we can use the x-coordinate to plug into my quadratic to find the y-coordinate. So this is going to be f of 1 is equal to 1/2 times 1 squared minus 1 minus 4. F of 1 is equal to 1/2 minus 1 minus 4. So 0.5 minus 1 minus 4 is negative 4.5. So my vertex is at 1, negative 4.5. So I just look over my work and double check that I didn't make any errors. It looks like I've done everything correctly. So once I get that, I can plot the vertex to start. So 1 and then negative 4 is here, so a little bit further than that, negative 4.5. It's right about here. So I plot my vertex, and I know this vertex, is it going to go upward or downward? Good. And why is it important that I check that before I do anything else? Anyone know? Well, it's not that important. It's going to save you time, though. What if this was going downward? Would it have any solutions? No. So you could save yourself the time of trying to find them. So then from here, we can use the vertex to create a table, like we did yesterday. So you're just going to sketch yourself out a little table, and you're going to pick some values. Now, what we learned about yesterday is you want the vertex to be in the middle of your values, and that's still going to be 100% true. So I'm going to pick the vertex to be in the middle. But what I know is, you can go back one number and do 0 and negative 1, and that's correct. However, I'm not going to do that this time. And the reason I'm not going to do that is because I know that my x value squared is going to have to be multiplied by 1/2. So I want those numbers to be positive so that I don't get decimals. So it's not incorrect to do that. I'm just going to try to get some more easier numbers to come up with. So I'm going to go back. I'm going to do 0, and I'm going to do negative 2 instead of negative 1. But if you do negative 1, it's still 100% correct. I'm just going to show you how you can kind of avoid the harder numbers to work with. And then we'll do, 0 and 2. So this is just a guiding point for you in your table when I tell you to pick numbers above and below. But as you get more comfortable with it, you can kind of pick numbers you know are going to work out better. So I'm going to plug negative 2 into my function. So that's going to be f of negative 2 is equal to 1/2. Wait a minute. I plugged in a negative, so this has to be negative, yeah. So 1/2 times 4 plus 2 minus 4. That's f of negative 2 equals 2 plus 2 minus 4. That's going to be 4 minus 4, which is 0. So right off the bat, I get 0 for my y value. We know this means that this is actually what? If I plot this, it's going to be here. What is this also? An x intercept, which is also known as a. So I found my solution, right? One of them. Because whenever you get your y to be 0, you know that's the solution, right? So I found my solution, which is what I was looking for after all. I don't really need to find this coordinate because we're not trying to graph it, we're trying to find solutions. However, we need to identify where my other solution would be, right? So that's where you have to use symmetry. Now you could go ahead and try to plug in numbers, but you don't have to do all that work because we have symmetry. So like I said, we know that our two solutions are always going to be equidistant from the axis of symmetry, right? So from here, the axis of symmetry is at 1, which means 1, 2, 3 units to the left of the axis of symmetry is one of my solutions. So 1, 2, 3 units is going to be my other solution, right? So in order to confirm this, what should I do with that x value that I just found? Plug it in, right? So this is going to be f of 4 equals 1/2 times 4 squared minus 4 minus 4. Well, that's going to be 16 divided by 2 minus 4 minus 4. That's going to be 8 minus 4 minus 4, which is 4 minus 4, which is 0, right? So 4, 0 is one of my solutions, and negative 2, 0 is one of my solutions. So that's how you can find solutions. So you don't need to finish your table if you find what you're looking for, okay? So if I'm asking you to graph a quadratic, yeah, you're going to need to finish a table. However, in this case, we're not trying to graph it, we're just trying to find solutions. So from here, you could draw a sketch of this, okay? But we found what we needed. So now we're going to move on to the next one. And what do you notice, what form is this quadratic in? It's in vertex form. So do I need to use the axis symmetry formula to identify the vertex? No. We can look at it and find the vertex, right? So what is the vertex of this particular quadratic? 1, 4. Good. So that means that I can create a table. Now we're not going to pick typical values because I see that I have a 1/4 in there. So I know my vertex is in the middle. So if I look at my equation, I see we're taking our x value, subtracting 1 from it, and then multiplying by 1/4. So I know that if I plug in 0, that's going to be okay to do. Why did I put an extra 0 on there? I don't know. Anyways, if we plug in 0, we know that that's going to give me a non-fraction as the first part. However, I'm going to end up getting a fraction down here when I add the 4. Yes?
How did you know 1/4 was the vertex?
You look at the equation, and this is in vertex form. So your h value is always your x component, opposite sign, and then the k value is always your y component. Okay? So from here, if I plug in 0, I see that I'm going to get a decimal in the end. So what can I make sure I multiply 1/4 by so that it's not going to be a decimal anymore? It's going to 2 times 1/4 is 1/2. So you're getting 4, right? So what x value will give me that? Well, if I make this inside equal to 2, I can get it to be squared. That's going to be 4. So if I plug in a 3 right here for x, that's going to work. So I want to plug in a 3. So like, this is kind of a hard thing to teach because it's more like intuitive. But if you're stuck on this, like you're not sure, you can go through and just graph the whole normal table we usually do, and then you can see about where the x's hit, and then from there you can kind of estimate and then plug those values back into your equation to confirm that they're solutions. So I'm going to plug in a 3. So let's plug in 3. So that's f of 3 is equal to 1/4 3 minus 1 squared plus 4. That's going to give me f of 3 is equal to 1/4 times 4 plus 4. That's going to give me f of 3 is equal to -4. I'm sorry, not -4. That's going to be -1. -1 plus 4. That's f of 3 equals 3. So I have a point on my graph. So far I have 1, 4, and I have 3, 3. Is this graph going to be up or down? Down. So right now I see that with a quadratic, if I have my axis of symmetry, if I draw my axis of symmetry in, we know that everything on that axis of symmetry mirrors itself, right? So if I have a point on the graph 2 units away over here, that means I also have a point on the graph over here, 2 units away, because symmetry, right? Now, if you were to draw a sketch of this so far with what we have, we can see here that it's going to kind of go somewhere like this, right? And to me, it looks like it's going to hit around 4 or 5. And possibly over here at -2-ish. So let's try to plug in a 5 and see what happens when we plug in a 5. Okay? So I'm going to plug a 5 into my equation. So that's going to give me f of 5 is equal to, what's 5 minus 1? 4 squared is? Yep. So 1/4 -1/4 times 16 plus 4. That gives me f of 5 is equal to -4 plus 4. What's -4 plus 4? So I have 5, 0 as a point on my graph. So we're pretty close with our estimate right here. So I know that 5, 0 is the solution. So we know something's a solution when we plug it into our equation and we get 0. Okay? So it's a lot of trial and error when you're using this method. Okay, there's really no way around that. It is using a lot of trial and error. So from here, I don't need to do the math for the other side because I can count its distance from the axis of symmetry, right? So this is 1, 2, 3, 4 units from the axis of symmetry. So over here, 1, 2, 3, 4 units over. So over here is my other solution, which is -3, 0. So it looks something like this, your quadratic. So sometimes your sketch is not going to be 100% accurate. You're just trying to gauge where it's going to go. So a few important things I want to talk about with this concept. It's very trial and error. There's not a lot of specifics I can tell you. You can make a table and keep going until you hit the x-axis or see where it's going to go, estimate where it's going to hit the x-axis and plug in your values. The main idea we want you to get from doing hand graphing like this to find solutions is to understand that when you plug an x value into your quadratic, the output is 0. That means that's the solution. Okay, that's the main thing I want you to understand. And I also want you to understand that solutions are symmetric across the axis of symmetry. Okay, they're this equidistant from the axis of symmetry. But like I said, we're going to move on to actually doing algebra to find these solutions soon. So this is more about your understanding of quadratics than you actually finding accurate solutions here. Because, like I said, it's very trial and error. There's better ways to do this. So we have a few more examples to try, but let's look at this first in case we run out of time, so that because those are try on your own situations. So we're going to talk about ordering the following graphs from widest to narrowest. So I talked a little bit about this with you guys yesterday, and you probably don't remember, but a quadratic is more narrow if that number is further away from 0 on the number line. And a quadratic is more wide if the quadratic is closer to 0 on the number line. So if we look at these, which one of those numbers is closest to 0 on the number line? 1/2, good. And we don't care about the signs because we're talking about distance from 0, which is the absolute value of a number. Because 1/2 is 0.5, right? Now, what would 2/3 be as a decimal, approximately? Yeah, it's about 0.6 repeating, right? So 0.6 is closer to 0, or 0.6 or 0.7 is closer to 0 than 5 is, right? And then lastly, we have negative 5x squared. Now something I want to show you is I'm actually going to graph these on Desmos so you can see what I'm talking about by this. Because if I tell you and don't show you, it doesn't really mean anything to you. Just a second. So the idea here is to understand that the A value controls the width, the stretch and compression of your graph. It's so slow. Okay, so if you look at our graphs here, we have the red graph is the 1/2, and you can see that this is the widest quadratic. Going down to the negative 2/3, all the negative sign does is actually just flip it over the axis. It doesn't change the width of the graph. Okay, the negative just flips it across the axis. If I were to take this negative out, it just goes upward, but it doesn't change the width. So as you can see, the blue one is the second narrowest, and then lastly, the most narrow one is the 5. So the bigger the number, the more narrow it is, disregarding its being negative or positive. So if we made these all positive, we could see here better the different narrow and widthness of them. Yes? No, the wider it is, the closer it is to 0. The more narrow it is, the further that number is from 0. You guys see what I'm saying? Okay. So I'll leave that one for you guys to try. And then the last few things I want to talk about are these two right here. Identifying the vertex by looking at a graph. So what would be the vertex of this graph right here? What's the coordinates? 0. Good. Yeah, you're right. 0, 1. Sorry. And then what would be the axis of symmetry here? X equals 0. Good. Axis of symmetry is always x equals your x coordinate of your vertex. What's the vertex of this one right here? And what's your axis of symmetry? Yep, x equals 3. And then last thing, how do we find the vertex of this one? We have to use, if we are in standard form, we have to find the, we could do that, completing the square, but we haven't done that yet. There's another way. The axis of symmetry formula. That's x equals negative b over 2a. So that's going to be x equals negative 4 over 2 times 2, which is negative 1. And then once I have the x coordinate on my vertex, how do I find the y coordinate?
Plug in X.
Good. I'm going to plug in x. So that's going to be y equals 2 times negative 2 squared plus 4 times negative 1 minus 3. That's y equals 2 minus 4 minus 3. That's y equals negative 2 minus 3, which is negative 5. Somebody grab the door, please. Thank you. And how about over here? So we have the h component of my vertex. Do you have a hero pass?
No, they didn't give me one.
They didn't give you one? Alright, I'll just mark it on your attendance. So this is your h value. And what would your k value be here if there isn't one? 0. So you can add a plus 0 at the end, which means that your vertex is 5, 0. So if you don't have a k value added at the end in vertex form, you can add it on by saying 0. So we have 20 minutes left. Does anybody want to see another example? This is easy, that part I think you guys can do. How did you guys feel about this? Finding the zeros? Not good?
Oh, finding the zero?
How did you feel about graphing it to find the solutions? It's not great, yeah, it is. But you guys understand the concept behind it?
Yeah.
You're just kind of like trial and error until you get something that works? Okay. Alright, so I'll stop here. Like I said, eventually we're going to learn a better way to do this. But for now, it's more about your understanding of the graph. So I'll stop the video.